All right, here are a couple of problems from the openstax textbook for chapter 29 on quantum physics. So the first one is about the photoelectric effect. So UV radiation having a wavelength of 120 nanometers, and we can see that from the chart here. 120 is much less over here than the 380, which is violet. So yeah, ultraviolet. Falls on gold metal, to which electrons are bound by 4.82 electron volts, and that would be the work function. What is the maximum kinetic energy of the ejected photoelectrons? And then here the answer, this one here, well, it's a photon energy, so which means actually the kinetic energy is just subtract the two from each other, which is 5.57. In any case, I'm actually going to show you that. So here's the solution. That's why I just said 5.5. We already know what the solution is. And so the kinetic energy of the electrons here that they acquire when they're hit by the photon is the original photon energy minus the binding energy, which again is the work function that is given in this case for a gold surface. And by the way, the 4.82, let me just look at that. I had a table here. Here it is. So we go 4.5 is what they're listing here. I'm not exactly sure why they're a little bit different depending. So anyway, subtract that, but let me calculate this one here first. In the top, the energy of the photon. So the energy of a photon is Planck's constant times the frequency. So I'm going to pull this one up here. So Planck's constant, 6.626, 10 to the negative 34. There we go. Times the frequency, but they don't give us the frequency, they give us the wavelength. So we use the wave equation. Frequency is speed divided by wavelength. So times speed of light. Oops, 3 times 10 to the 8th, there we go. Divided by the given wavelength, which is 120 nanometers. I'm going to put that in parentheses. 120. And that would be in nanometers, so I'm going to put a 10 to the negative 9 right there. Should work. Close the parentheses. There we go. That would be the energy in joules, and I divide that by the charge of the electron in order to convert that to electron volts, which is the typical unit used in atomic physics. So 10.34 electron volts. I know the solution says here 2.359. Again, maybe they round it, maybe I round it. Oh yeah, they used 6.63. I used 6.262. Okay, and from that I subtract then the 4.82 that are given in the problem, and that is again the 5.52 in this case electron volts. All right, give myself a little break here. All right, so this kind of problem here, it's similar, but the algebra is actually now backwards because it's asking for the wavelength, having given the kinetic energy of the electrons and, well, the binding energy or work function for potassium. So find a wavelength of photons that eject 0.1. It's basically also the photoelectric effect. They're just asking for a different thing here, which is the wavelength of the incoming photons. So let's see, I'm going to actually look up potassium here. Where is it? Where is it? There it is, 2.3, and I think that's what they said in the problem, right? Yeah, there you go, 2.24 electron volts. So that's what we're going to use. Figuring out what the wavelength is. And so I'm going to already go to the solution. They did a certain kind of algebra here. I'm just going to do it a little bit different. I should come up with the same result there. So here's what I'm going to do. I take the given 2.24 electron volts for the binding energy for potassium, and I add the kinetic energy that they give us for the ejected electrons. So that one there, 2.34. That's in electron volts. Now I'm gonna convert that to joules. So here we go. Notice they did the algebra all in one step here. I mean, they did the algebra first and then they do it all in one step. I kind of like go backwards and chop it up. So here's the energy of the photon in joules, and that I divide by Planck's constant, which then will give me the frequency of that photon. So divided by this one.
There we go. Very large frequency. This is, I think, in the trillions, like 565 trillion hertz. Yeah, they have relatively large frequency for visible light. Or typical TV or radio signals, they're like in the megahertz and maybe gigahertz, but they're also in a completely different part of that electromagnetic spectrum. Okay, anyway, here's the frequency. To get now the wavelength is speed is frequency times wavelength. I have the frequency now, so I divide that into the speed of light. Yep, there we go. So speed of light is 3 times 10 to the 8th divided by my answer here. There we go. And then finally, this one is actually in meters, so I multiply by 10 to the 9th. This, again, is actually 10 to the 9th. 1 times 10 to the 9th is actually what it says, in order to get in nanometers, and there's the 530.3, which is basically the same thing, 531. Again, I think they rounded Planck's constant to 6.63, which I didn't. So that would be the answer to that one. And that would be actually it. These are the only 2 problems I had for chapter 29. All right, so here are a few problems using the Bohr formula for the hydrogen atom, and there's a reason why it's the hydrogen atom exclusively, actually, and that is it only has 1 electron. And more to that, about that and the other elements a little bit later. In any case, here we have the electron jumping down from a higher orbit to a lower orbit, and of course, as it's losing energy, it has to give that kind of energy off, which would be then the photon here. F for frequency of the photon. That's kind of a weird thing to say a photon, to show, yeah, a photon. Anyway, when it jumps down, it can jump to the first, second, third energy level, whatever, and they have certain names. The first one would be the Lyman series. So for the Lyman series, if you come up with numbers in this kind of region, you did it right. The Bama series, which is in the visible light, 365 nanometers, that's actually already in the ultraviolet, but starting around 420 or so, that's really then violet, and then 656, which is the end, at the end of the red part of the visible light spectrum. So this one here would be when it jumps down to the second orbit, and then the Paschen series when it jumps down to the third orbit, and that would be in the infrared. And then there are more which are over to the right, and they would be less likely. Okay, let's do a few calculations here. And they all use the same formula. Here it is, the Bohr formula. So I'm going to have the Rydberg constant times the 1 over one of the orbits minus one of the other orbits, both of them squared, and then figure out what the wavelength is and perhaps convert to nanometers. Okay, let's get started. So by calculating this wavelength, show that the first line in the Lyman series is UV radiation, and then the answer is the wavelength, which is way less than 380 nanometers. So let's calculate that using the Bohr formula. So here we go. The Rydberg constant, 1.097. I have to look that up. 10 to the, let's see, 7. Yep. It's one of the few things that I don't have memorized. Times, parentheses, 1 divided by 1 squared, because it jumps down to the first orbit for the Lyman series. And then it says the first line in the Lyman series, which means it jumps from the second orbit. So 1 divided by 2 squared, parentheses, enter, then take the reciprocal of that. There we go. And now I actually have it in meters, which means I have to multiply by 10 to the 9th, and that's the way to write it, 1e9, and there it is, 121 or 122 nanometers rounded, which indeed is less than the 380. Okay, let's go to the next one, and I already have them prepped actually here. So here's the one I just did, number 7. So number 8, find the wavelength of the third line in the Lyman series, and we can already see the answer, so it's basically the same thing. I'm going to clear this one here and go back let's see how many steps, 3 steps here, there we go. And now it says the third line in the Lyman series, which means the second line would be it jumps from the third orbit, the third line would mean it jumps from the fourth orbit, hence that's where they put in the 4. We can see that over there. And this calculation, by the way, that's a little bit too complicated for me. I just plug it in just like this one over here. And then I still have to invert. Okay, and anyway, here it is. Root back constant there, and then here this one is a 4 instead, 4 squared. Then I'm going to invert the answer, and I'm going to multiply times 10 to the 9th right away. So do not write 10e9, because that would be actually 10 to the 10th, because this one is 1 times 10 to the 9th. That's what that means. So I converted right here to nanometers, and there it is, the 97.2 nanometers, just like they say in the in the solution here. Okay, next one, still Bohr model for the hydrogen atom. What is the smallest wavelength line in the Bama series? So for the Bama, it jumps down to the second orbit, and the smallest wavelength line, I'm going to go back over here, would be actually this one here would be the smallest wavelength, so we ought to come up with 365, and that's when it jumps from a very high orbit. So I have to compute that. So here we go. Start over again. Go 2 steps back, because I already had it plugged in there. There's the Rydberg constant. Now it jumps down to the second orbit for the Bama line. There we go. And that says from the... Oops, made a mistake there. How did I do that? Oh yeah, no. 2 squared. There we go. Minus 1. Well, from a very high orbit, so technically that's close to infinity, or maybe I plug in 99, we're just close to infinity, right? Or 9,999, that kind of thing. In any case, the second fraction gets so small that it's virtually 0. So I'm just going to fix this one here to make a 0 out of it. Again, from a very high orbit. And if I plugged in 10,000 there in the denominator, it's still so tiny when I subtract it from 1 minus 2 squared that it's virtually the same thing. So hit enter. There we go. Then go back, let's see, 2 steps again. And there we go. So invert that result and get it to nanometers. And there it is, 365 nanometers rounded, just like it said. All right, let's see the next one. Show that the entire Paschen series is in the infrared part of the spectrum. To do this, you only need to calculate the shortest wavelength in the series. What they mean by that is that when I look at the Paschen series here, is the shortest one is just this one here, the 820. So if I calculate that for a very large orbit again, I come up with that, yeah, all of them ought to be in the infrared. So here we go. In fact, there's the 820 right there. So here's the calculator. I have to find it. There it is. All right, go back. Oops, I didn't mean to do that. Go back 2 steps right there. And now it jumps down to the third orbit right there. Go back, let's see, and convert to nanometers. And there is the 820 nanometers. Let me just show you that I said earlier, either the second fraction is virtually 0, or you put in a very large number there, so such as this one. So here I'm going to put, yes, it jumps down to the third orbit for the Paschen series. And now from the very high orbit, let's say I'm going to put in 999 right there and square that, parentheses, and I hit enter. And again, I'm going to go back there, right there, converting to invert and convert to nanometers. And again, I come up with the same 820 nanometers, just like I did before. Any other spectral line for this one here for the Paschen series, by the way? Let me show you that too. This one here, so it jumps down to the third level, and let's say it jumps down from the sixth level, for example. So I'm going to plug in the 6 here, and there we go. It didn't ask for that, but here it is. And again, convert it, and 1093 nanometers, which is larger they're not wavelengths, so also in the infrared. So I already had computed the smallest wavelength, so anything else would have to be in the infrared as well. All right, so do the Bama and Lyman series overlap? To answer this, calculate the shortest wavelength Bama line and the longest wavelength Lyman line. Let's see, calculate the shortest wavelength. I'm going to go back to this diagram here. So the shortest wavelength would be this one here, the 365, and I already did that earlier. And then the longest one here would be 122, which I also did earlier. So I think we can safely answer, say, yeah, there it is, 365, 122. And the way to do that is, yeah, do this one here. I'll do it again. So here is going to be for the Lyman series. So I'm going to put a 1 here, right there, and the 2 over here, because that would be the least amount of energy. Oh, the 2 is right there. This is the square. So this would be the least amount of energy. And again, I'm going to get a couple, convert to nanometers. There's the 122 again. And then the largest energy from the Bama series is when I go here, down to the second orbit, and then divide this one here by 1 over 99 squared. There we go, parentheses. And then again, convert. There we go. And that's the same 365 nanometers that we already saw. All right. I'm going to take a little break before I do this last problem here. I believe this is the last problem here for this particular chapter. And then I have one from the next chapters as well. All right. I looked at this one. I had to familiarize myself with this one again. I'm going to push this to the next page because I do need a little bit more space when I'm done. One moment. There. Oh, shoot. Sorry. Oh, geez, there it is, there it is. It needs its own page. So it says the wavelength of the 4 Bama series lines for hydrogen are found to be this much. And when it says are found, I'm assuming that they mean it's actually measured in the lab. And I just did that in my Physics 124 lab a couple of weeks ago. And students came up with really close results to that. And then it says, what average percent difference is found between these wavelengths and those predicted by the Bohr formula? It is amazing how well the simple formula disconnect originally from theory could duplicate this phenomenon. What it means here, disconnected originally from theory, is that Bama himself came up with that 30 years before Bohr figured out what the theory is actually, and he just played with numbers, I assume, and came up with the right results, but didn't know what was behind the numbers, why it worked, and that's what Bohr came up with then 30 years later. I'm talking about 30 years before, 30 years after, between 1880, that was Bama, and Bohr was around 1910. All right, so let's compute the numbers here. And they're saying, okay, using, this is actually the solution here already, using these numbers here yields these wavelengths, and I have no idea what happened here. This is from the solution manual, because that's not what you get when you plug in the numbers. Really, I don't know. So I'm going to show you how you get these 4 first Bama numbers. So here we go, back again to the same thing. And here we go, here's the Bama formula, and the first one is going to be the 3rd orbit. There we go. That's how it jumps down. And I'm going to save myself a step, and I'm going to put a parentheses in the front. I'm going to put a parentheses in the back. Put it to the -1, which means I inverted already. And then I multiply with the conversion to nanometers, so I only have 1 step. There we go. Enter. And there it is. There's the 656. I don't know how they came up with 600 right there when they plug in n equals 3. Now, n equals 4, I do agree with that, because I will also come up with that. Go back a little bit here. If this was at the end of the formula, it would be a little easier. There we go. Enter. And there it is, 486. Yay, they got the right thing. And then I put a 5 in. there, 434, and then I put a 6 in. And these would be the first three that I just computed. The 656 is the red line. The 486 is the blue or turquoise line or aquamarine. The 486 is the violet. I'm sorry, the 434 is the violet line and deep in the violet. And then this one here, the 410, is also so much in the deep violet that the human eye actually cannot perceive that. In any case, last two here, 434, 410, I have no idea how in their solution manual they came up with these numbers here. And then they compute the, I come up with these. I don't know if I wrote this one here. No, because known wavelengths. So that must be part in there too. I think this one is just repeating what it said up here. In any case, I do not come up with these large errors here of 8.5% or so. Yes, 0%, yes. In fact, all of mine are going to be in the neighborhood of 0%, not 6.5%. So if I took any of these here that I just computed, 656, 486, 434, and I compare them to the ones that are listed up here, 656.5, 486.3, I come up with really tiny errors in the neighborhood of like 0.1% or so. Again, I don't know how they came up with the wrong answers there. Going over here, that means, yeah, in fact, here I wrote it down, percentage errors, whatever it's percentage, and so on and so on. Usually, which are probably achieved, spelling error, I have to fix this one here. Students usually get, I have to actually put something in here too. They do get a small systematic error, but I have to put something in there. Anyway, 0.03, 0.02. I will calculate the first error here. So 656 compared to 656. And this is the way to do it. 656.5 compared to 656. Ignore the 1 in the front. And then the percent would be here. This would be 1%. This is point something still. 0.07 or 0.08% would be the answer in this one here. So again, I don't know how they came up with that percent. All right, yeah, and my students, I want to say they get in the neighborhood of like about 1% error. I remember that from 2 weeks ago. Oh, that's what that meant actually. I meant to type a 1, not an exclamation point. Okay, here, by the way, are the lines for the hydrogen visible light part. So here's the red 656, the turquoise, aquamarine, call it whatever color, 486. This is the 434 in the in the violet, and this violet one here at 410, the human eye can barely perceive, if at all. All right, earlier I said something about the hydrogen atom over and over again, and you will find it in all of quantum mechanics. We do the hydrogen atom over and over again. We never get to any other atom. And here's why. The hydrogen atom has special significance, quantum mechanics, as a two-body problem physical system which has yielded many simple analytical solutions in closed form. Copied that from Wikipedia. It's a correct statement. And thus, when studying, and the following I wrote, when studying quantum mechanics, one comes across the hydrogen atom much more often than any other element. However, you could say that ionized helium plus, so if you remove one electron, you have helium with one electron, or if you remove 2 electrons from lithium, then you have lithium with 1 electron, or if you remove 25 electrons from iron, then you have iron with 1 electron, in which case you have a simple two-body problem, just the nucleus and the electron, and now you can do it again. But these ionization requirements would be very rare in nature, so you would find barely any applications for that. The quantum mechanics, of course, likes to deal with other, in any kind of atoms, molecules, and so on, but it really becomes very tough. And so here, well, quantum mechanics is already involved. One can imagine how complicated it gets when applying it to atoms and molecules. For example, while computing the ionization energy for hydrogen is a one-liner, and that is 0 from earlier, you know, it jumps all the way, or jumps all the way out by absorbing a photon. And so the second fraction is 0. I'll show you that in just a moment. In the Bohr formula, see the helium, and I'll get there to the helium in just a moment. So let me just show you this one here, hydrogen ionization energy. So again, the Bohr formula. There we go. Hold on. Wait, that's not it. There we go. So here it jumps down to the first orbit, and then here again I would have a very large number right here. So again, I'm going to put 999 in, and then I convert it to nanometers already and take the reciprocal of that. So that would be the 91 nanometers for that. And now I would have to do the following. I have to speed of light as frequency times wavelength. So the frequency is the speed of light divided by the wavelength. There we go. Oh, and convert back to meters actually, not nanometers. So that's a very large number. There we go. That's the frequency. Multiply by Planck's constant to get the energy. Let's see. There we go. And divide by the electron charge to get into electron volts, which is the typical thing to use for ionization energies, and that's a famous 13.6 electron volts, which I'm going to try to show somewhere here. There it is, right in front of us. There is the 13.6 rounded electron volts. That's the hydrogen's ionization energy. And now I'm going to show you, you saw what I did on the calculator. Yes, it looked a little involved here, but you know, that was just about a one-liner. I'm going to show you, let's see, I have to find it, this one here, this paper. I have to scroll back a little bit. Starting here, ground state of the helium atom, figuring out the ionization energy for helium, and because it has 2 electrons, this just goes on and on for the next 5 pages. And you can see all the calculus. This is called the calculus of variations. And this is it. This is what you actually would need for the figuring out the one for helium. And I think the solution is, I think I might have already scrolled past it. I think I did. Hold on. I'm going to give myself a break trying to find it, actually. I saw it earlier. Right, I kind of found it. It's actually here. So this is the energy eigenvalue from which this 2.85, from which the correct ionization energy of 24.6 electron volts derives. And again, what I wanted to show here is that for anything but hydrogen, it becomes really tough to do quantum mechanically, and that is why in quantum mechanics we quite often just reduce ourselves to using the hydrogen. All right, that's it for this particular chapter, and then I'll do one more chapter in a little while. All right, just a little more here. So the 2.85 here is also called the Hartree, and that would be here actually. So yeah, named after Hartree. So 2.85, which then to converting it to electron volts is 27.2. So I'm going to do that. So 2.85, a better number by the way is 2.90 times 27.2. So that's going to be in electron volts, and that is 77.5, or a little better actually, 79.0. That would be the ground state energy for the helium for both electrons, and from that I subtract the ionization energy of the second electron once the first one is removed, and that's relatively simple. It's 4 times the ionization energy for the hydrogen atom, 4 times because it's 2 squared that goes into the formula,
2 being the number of protons in helium, and there's the 23.1, which I did find earlier. Let me see if I find it again. I did find it earlier. It was on hyperphysics, I think. So hyperphysics, ionization, energy. There we go. Let's see. There we go. There it is, close to 25, and that's what I just computed a moment ago. We can see that here. There's the 25, so close to 25. And again, that's what I actually calculated right there. Again, it's actually a little bit larger. Okay, that's finally it. So here are a few problems for chapter 31 on nuclear physics. And the first one is a conceptual question. I let you look at that, and the answer is already provided here. A physics student caught breaking conservation laws is imprisoned, and then she leans against the cell wall hoping to tunnel out quantum mechanically, and then the answer is, well, according to the uncertainty principle, she would have to borrow so much energy that the time that both of them are part of the uncertainty principle, energy times time, is in the neighborhood of Planck's constant, that time would be just way too short, much shorter than anything ever measured. And besides that conceptual question, this little video that you see down here has nothing to do with that, but it reminded me of this Western comedy where there's a prisoner going to cell where there are no bars, which is what it says here. Anyway, worth watching that little scene. Okay, so I'm going to do this one here. This is about binding energy, and I'm just going to pull up the solution already. Here it is, and plug it into the calculator. So to figure out, oh, actually, let me get back to the original problem. So it says that the 56 iron isotope, that means it has 26 protons and 30 neutrons, is the most stable of all nuclides, or has the largest binding energy. And when we look at this graph here, and this is actually from the openstax textbook, you know, and you can see this graph everywhere for the binding energy per nucleon, then iron certainly is on the top. Prior to that, because the binding energy is less, fusion actually would be advantageous here. You would gain energy, and that's what stars are doing. They're fusing lighter elements into something heavier. And then beyond that, actually, it's fission. So way over here would be uranium, and when you fission that, it gets actually to a higher binding energy, the two nuclei that result, and you set energy free that way as well. So in any case, iron itself, the 56 isotope, is the one with the largest binding energy. And when we look at this graph here, then we can see it's relatively close to 9, so about 9 mega electron volts per nucleon. That's kind of what we have to expect. Now let me go to the solution that's already here. In order to figure that out, I would have to calculate, and I will, the mass of the 26 protons that are inside, and the mass of the neutrons inside, the 30 neutrons inside, and add those together, and that should be, and I'm just copying, obviously, just copy these numbers down. You can look at them anywhere in the book or in reliable physics sources. Notice again, the neutron is a little bit more massive than the neutron. I'm sorry, the neutron is a little bit more massive than the proton, because it is, when it decays, it actually decays into a proton and electron, so it has to be a little bit more massive. Okay, so this is what the mass of the iron nucleus should be, 56.46, but it's not. The iron nucleus measured is actually that number here, the 55.93, and so on. So I'm going to subtract that. And the mass deficit that we have here, that is being used for the binding energy in order to keep the nucleus together. So that mass deficit of 0.52901. And then we convert that to
the mega electron volts, and notice that it's mega electron volts per c squared, and then we have another c squared over here. This one is then from E equals mc squared, and then at the end, because it's per nucleon, we divide by 56. So first I'm going to do times the 931, and again that conversion factor between mega electron volts and joules, you can look that up, and that one is it, 931.5, and then divided by the total 56 here, and there we go, 8.799. Let's see what they got. Yeah, 8.790. Maybe I round it, maybe they round it. In any case, that's really close to the 9 mega electron volts that we saw on the chart per nucleon. All right, I'm going to give myself a little break before I go ahead with the next one. All right, the next one is pretty much the same kind of calculation. So I'm going to just repeat that. So this one here says 209 bismuth is the heaviest stable nuclide isotope. And when we look over here, oh, that's actually off. There we go. When we look over here, we can see mercury over here, and then we would have, shortly after, we would have lead, and then bismuth is actually one more. And then beyond bismuth, well, that's where we have the rest of the radioactive elements, or many of them, including the uranium and the radium that we see here. So in any case, the bismuth 209, so that's what we're going to compute. Oh yeah, and then actually, since it's over here, we kind of look at it and see like between 8 and 9. You know, definitely less than the iron. Okay, that's why the iron actually is the most tightly bound, as it said. It has the highest binding energy per nucleon. The other one is the heaviest stable isotope, so not the same thing. All right, so here's already the solution for bismuth, and then when I plug in numbers, let's see, here we go, and I'm going to clear this one, and I go back a few steps because then I don't have to type so much. There we go, that should work. I wouldn't know 83 for bismuth top of my head. I would actually have to look that up too. And then here's the proton mass, and then the number of neutrons. Subtract 83 protons from the 209, and you get 126 neutrons. And again, if we put these 83 protons and 126 neutrons together, we should get an atomic mass of 210.74, but the bismuth 209 is being measured at 208.98, so somewhat less. So we subtract that. Oops. 208.9, and so on. All right. Okay, there's a 4. All right. Enter, and then the same conversion as earlier with the 931. There it is, but this one, of course, is 209. And we come up with 7.84, which is, when we look at the chart, yep, somewhere around there. This looks kind of like around 8 or so. It's a little bit hard to see. But in fact, I think the bismuth is actually kind of here. So that could be quite correct, yeah. All right, that was actually it for this chapter.